brings.
Thank you very much. Can you hear me? From my perspective, I don't know. Okay, so it's great that I am able to give talk in Poznań, in Będlewo. Thank you, organizers. And I decided to talk of something which maybe first my dream. So my dream is that really Chobanov homology, whatever it is, will measure some phase transition in some physical problems. This is very far from being realized, or even the path is not clear. I think the path is from what I call Young-Baxter homology of Young-Baxter operator, whatever it is. This part is maybe possible, but is doing. So my plan was really to show how to define precisely Chobanov homology for people who don't know, just from scratch. This will follow Oleg Wilo method. So first of all, when Chobanov homology was invented or constructed, so we know it was 1997. Chobanov was just fresh PhD, planning his trip to Paris from US, and he was stuck at airport. This you can know. With my case, that is standard story, that he was stuck only for 3 hours. But still, this was enough for him to have idea of Chobanov, of his homology. So maybe first I will formulate conjecture and theorems, and I will go to some combinatorics, because this combinatorics is very much like this discrete Morse function talk, and some results are similar. And then last half an hour I will spend on precise definition of Chobanov homology after Wilo, so we'll know what I'm talking about. Maybe it will be inverse order, but first kind of general philosophy, etc. So general philosophy, it is well known. It is known that computing Chobanov homology is NP-hard. Not only Chobanov homology, but some special cases NP-hard as well. How we know this? Again, slogan Chobanov homology is categorifying Jones polynomial or Kaufman curve. More classical, still new, but more classical invariant of knots. So maybe better to use language that really Euler characteristic of Chobanov homology is Jones polynomial, or rather this Kaufman bracket version of Jones polynomial. So let me write this as slogan. So homology Jones polynomial. So what is the setting? The setting is always that we have link in S3 here, or I3. So Jones polynomial in Kaufman bracket version. So of course, it's more general than Jones polynomial, and it was proved pretty early, so maybe some dates. Jones polynomial is 1984, Kaufman bracket year later, and year or two later, Francis Jaget, French mathematician, French combinatorist, proved that computing Jones polynomial and related polynomial is NP-hard. And not only Jones polynomial, but almost all substitutions of Jones polynomial. Exception was invariant justly called determinant you can compute in polynomial time, and few other substitutions which can be recognized as related to homology of branch covers of S3 with branch set link. So something which classically computing this homology was polynomial. All other substitutions are NP-hard, So up to famous conjecture is not polynomial, or up to subconjecture is really exponential. So I will talk about this later when I will define formal Chobanov homology, and I hope to give all the details. But this is the status. Generally, there is no chance for polynomial complexity of computing Chobanov homology, because even Euler characteristic is difficult. But of course, there was need to compute John's polynomial, historical John's polynomial for bigger nodes. Otherwise, the limit was more or less 50 crossings. And many interesting examples were related with not with 100 or 100 log crossings. In particular, so-called mutation, not biological, but not theoretical mutation, some modification of diagram, which was preserving John's polynomial. To show that this not really different, using John's type polynomials, require computing, I think, 99 crossings. So this was, I think, first observed by Morton and Scholt. But they just wrote problem, they had to think. No. So what they notice is that if you restrict yourself to the given number of strings, so first of all, when you have not or link, you can change this into braid form. Let's say 4 braids. That's enough. So this is braid. Braid will be 4. What is this group of such pictures? In fact, was first recognized as important already by Gauss. Gauss, in one of his notebooks, without the date, drew similar picture of 4 braid with comment. It is a good way of analyzing nothing. So he knew what he was doing, but there was no follow-up. In fact, this page was forgotten and is not in his collected works. Anyway, so this was recognized. You can try to make braid out of the knot, which is not difficult. It was done by Alexander in the early 20s and even by Brun in 19th century. Slightly different language. Anyway, so you can think that we have our knot in this braid form. So this is braid, and then you can close this. So for the only then it is a knot or a limit diagram. Anyway, what they notice is that they restrict themselves the given number of strings, then computation can be of polynomial complexity. And they needed it for 9 strings, so they wrote a program specifically for 9 strings, which was rather big, but polynomial below, and succeed. So maybe I write it here, computing John's and values generalization, confident, totally Kaufman, one bracket in particular, John's polynomial. Or a braid, or a closed braid. It should be already in this form. Or closed braid. Even fixed, say fixed. Strings. That's complex. This is a practical algorithm. It is rather easy. Probably computer science language is called dynamic programming. You just keep records of smaller calculations and essentially quadratic. So would be natural to conjecture this what we do, that for Chobanov homology the same thing holds. So this will be our kind of main conjecture. Chobanov homology Strings. Polynomial. Complex. So this I will keep this kind of conjecture. So this would be very useful in practice because there's
Can I just to make this clear? For every link that you consider in S3, this theorem says that if you consider the Brady.
so you can change the grade, but now consider grade. Yeah.
the
With
Brady-
given number of strings. So
So
this is,
up to 9, it is polynomial.
no, I mean up to 9 it is. Yeah. For polynomial, no. You fix n, and if you consider only n grades, it is polynomial. The degree of polynomial is really growing with n very quickly, but it is polynomial.
So that 9 was the number of the string that it makes it polynomial.
Yeah, exactly. Fixed number of
Yeah,
strings.
exactly.
And of course, this is exactly, exactly the same for Chobanov homology as conjecture. Very natural conjecture. So maybe I should, before this, I should say that most of the things I'm saying, including this conjecture, is with Maritania's error.
You consider links, not the nodes, yeah?
There's no difference in fact.
No, okay.
And in fact, when you compute it, then we make links with nodes. So So in fact, people try to have reasonably quick algorithms for Chobanov homology, particularly Manhattan program, etc. So they didn't succeed with anything quicker than exponential. The fight was exponent, but not better. So when we start this program, we're rather optimistic that we're just trying to follow rather easy, molten short dynamic programming if we went, but no. We didn't succeed. So what you do when you don't succeed in general conjecture, try to kind of eat it partially. So two possibilities. One was a strict number of strings. And of course, my subtitle already suggests that we succeed only for short grades. And even less, not full Chobanov homology, but only part of this. So we succeed in very narrow setting, but polynomial growth algorithm, and even this can be rather difficult. We will not succeed if we don't go to very nice algebraic combinatorics. So maybe I should just write some notation in this conjecture. So Chobanov homology will have two grades. So H and B, I'm using a plot of 0, so H and B. B is really will be fixed. If you fix B, we have standard homology. And when I say extreme, I will define in which sense that we fix the second coefficient. What is B and H? If often it's called quantum dimension, this homology. Anyway, so we succeed only with short grades, and not with full Chobanov homology, but only special grades. But still, we can compute it from that. So I think now I will go to combinatorics, which for some of you may be interesting. And it really looks like literally calculation for discrete Morse story. Nothing strange. So let's go to combinatorics. So I will go back to Chobanov homology later, but mostly to have formal definition. Now formal in combinatorics. So I think it was even mentioned in his talk. So if G is a graph, you can construct many simplicial complexes from graphs. Of interest for me is what most of the people call independent simplicial complex, meaning if vertices are not connected by edges, then they form simplex. Then independent simplicial complex. So now, more finally, vertices of this complex are the same as of the graph G. And say V0, Vm. Vertices of G or vertices called simplex. If there's no connection. No connection. Independent simplicial complex, and we analyze homotopy time of this complex. So maybe examples, and historically important that people start to show very simple examples that trivial, but to start from some. So let Ln, maybe it's not standard notation, will be line graph or path. Line graph of and edges, yeah, and both edges. Or something like this. Okay, let's find this independent simplicial complex for line graphs, experimental. So, what is independent simplicial complex of L0? And L0 is just vertex, so of course it's contracted. Okay, L1 interval. So we have two vertices, but because they were two here connected, the simplicial complex are not connected. We get something like this. Two isolated vertices. And you can say that triviality, but it's interesting because we know you can interpret this as zero-dimensional string. Okay, let's go further. L2. So we have three vertices, and this edges will be not in the simplicial complex of the line graph. So what survive is not much. So interval and dot, not homotopically, it's again as zero. It's homotopically equivalent as zero. Not yet enough to have any pattern. Let's go further. Independence complex of L3. What is this? This L3, so we have four vertices. And what is connected now was not connected before. That is disconnected here. Disconnected here. Second is connected with the last one. The third is connected to the first. It's already connected. The fourth is connected to the first and to the second. So that's it. Contracted. Equivalent to 4. Maybe more for pattern. maybe this is it. Okay, to see for pattern, maybe L4 and L5. Fine. So what we have? L4. So now we have this triangle. We have notation V0, V2. So V0, V2, and V4 form a triangle. The only triangle. So let's start drawing from this triangle. Let's say V0, V3, V2, V4. Okay. Then what about the V1? V1 is connected with V3 and V4. This is going to V1. V1 to V3 and V4. What about V2? V2 already we have all connections. V3 is connected to V0 and V1. V3 is connected to V0 and V1. So it's like this. Is it anything more? We analyze everything, but let's go to V4. V4 is connected to V0, V1, and V2. V0, V1, and that's it. So there's triangle and kind of. But homotopically, we can of course shrink this triangle, and this will be homotopically valid to S1. Then probably we can go for V5, but I will not do this. What we have done. Left on this lemma. It's Kozlov. Maybe there's some relation. The first name. So he showed, I mean, what we see already clearly from the pattern, that independence complex of Pn is equal either contractible, contractible, it was for 0 and for 3, when n is divisible by 3. And this is a sphere of dimension k. So it is the same dimension before, I think, let's say for 3 and 4. For 3 was contractible, for 2 was still. Yeah, so it would be n equal 3k plus 12 or 3k plus 2. I think it agrees with our calculation. So he noticed such things. So this was, I think, the first concrete calculation of the general class of graphs. So I would like to make another calculation. Maybe this is not needed for polygons, but maybe I will do it quicker. There is a laser, yeah? Others here. So maybe before I go to polygon, comment about the realization of line graph. The realization here is 3 or 4. So in the same paper, he proved, Kozlov proved that. So maybe it should have A, B, and C. B very shortly. A forest. The same result hold. Meaning it will be either contractible or homotopically valid to one sphere. independence complex of T. I will just put it homotopy equivalent to a cell. Dimension of the cell depends on the structure. And he proved as well theorem for polygon. If Pn n-gon, then Pn, the independence complex of Pn, is homotopy equivalent. But I will not write result, because I will do the last calculation for today. Small examples of polygons, and try to have his formula from data. Okay, so how early to start? Maybe let's start from two-gon. Of course, the fact that there are two edges connecting vertices is irrelevant, because independence for not being independent is enough to have one edge. So this the result here is like with one edge, and this we already checked. It was S0. Maybe triangle is interesting. Is giving different sort of result. So what we get? Of course, because everything was connected to triangle, nothing is connected to independence complex. So this is what we get. So maybe it's not what we get is interesting, but how we interpret three dots. We can interpret this as a wedge of zero-dimensional spheres. 2 points connected by 1. So it is wedge of S0 and S0. So that is something richer than for forests. Okay, what is I for I squared? Square we can do quickly. So only diagonals are not connected before, so this is our result. And this is, of course, homotopy equivalent to S0. Okay, so maybe something richer. 5. Picture. Unlike line graph L5, here we don't have triangles. This should be still rather easy. Every vertex we have degree 2, and we get the star. And pentagon is the form of star. Let's draw this. So this and this, this and this, and of course the last one. So clearly the circle. Maybe not even homotopy equivalent, just as one. So what we got? Zero-dimensional sphere, wedge of 2 zero-dimensional sphere against zero-dimensional sphere with 1-dimensional sphere. What you should get for C. This is the last calculation I will do. This is a little picture. Notation 0, 1, 2, 3, 4. So what we see here, that we have two triples of independent vertices. Of course, V0, V2, and V4 will form one triangle, and V1, and V1, V3, and V5 will be another triangle. So just to draw this sensibly, let's start from bottom triangle, and this is a triangle. And let's call this V0, V2, V4. Let's look at V0. It has one more connection. It is V3. I will draw this V3 above as the beginning of the next triangle. V3. Okay. V2 has additional connection with V5. So let's draw V5. And finally, V4 has additional connection with V1. Okay. And as was mentioned, an obvious V1, V3, V5 for the triangle. Okay, and that's it. This is our figure. But of course, it's nice. In fact, we did see this in the previous talk already, this simplicial complex. But homotopy equivalent, it is, let's have three triangles. Then let's write this as this. Of course, this is wedge of S1 and S1. So you see the pattern. I will not go further, enough to have pattern. So if n, this number is divided by 3, we have wedge of 2 spheres. So it is x, right, k minus 1 is around k. Okay. This one. This one, if n equal to k. So for example, for k equal 1, for a triangle, this is 0 plus 0. Okay, and then it is S. So this is enough for the people. Connecting without thinking, but it follows from the pattern. K minus 1 is n equal to k plus or minus 1. So this would agree with our calculation that when we have, for example, S1 and S1, so below it will be S1, we computed, and above we didn't compute, but 57. Anyway, these are these very early theorems by Kozlov. So, in fact, this is kind of generalizations of this are key to any calculations of independence complex of graphs. But there's one theorem which does not follow from Kozlov or something similar. So maybe I will write this. I don't like to spend too much time. It's okay. I don't like to erase. Okay. So there's a very nice observation by Solba and another combinatorics. I do like combinatorics, so it's a student of Gjorner, student. And with Mauritania, we slightly generalize this because we need more general form. Well, the best thing to explain is drawing. So let G be a graph with half of length 2, like on the picture. So there's one vertex, then path of length 2, and then another vertex. And then we contract whole path. So contract whole path. A standard contraction, but not of one vertex of whole path. So this is the result and call this G. Then it happened that independence complex of G is suspension, is homotopy equivalent to suspension of independence complex of G. So whenever we see graph of length T, it does reduce. Okay, let's do then independence complex of G is equal suspension of independence. And what we see, we did see this phenomenon here. This periodicity modulo 3 for line graphs and pentagons is really following the solver lemma. There is no need for general calculation. You reduce line graph to either one vertex, one edge, or two edges, or pentagon to two-gon, triangle, and square, which I did. So having solver lemma, we can recover this Kozloff theorem immediately. And maybe the last thing which we use analyzing this independence graphs is rather easy observation, but I will formulate this. This calculation. So kind of general observation. If V is a vertex of any graph, so we have any graph and any vertex, and now big assumption, independence complex of G minus star of V. So we have not only V but its neighbors. And if this is contractible then independence complex of G is equal to independence complex of G minus V, which suspension of independence complex of G minus star. Look serious, but it's very easy exercise following just in definition. Just imagine what independence complex and what means star removing and what means vertex. But I will not use it, but will take another 5 minutes. I will just say that, for example, from this lemma, very easily you can compute and prove Kozloff theorem about forests. Because whenever we have leaf, not even necessarily forest, but just individual leaf, then if you take W out, it has isolated vertex. So independence complex will be the con, so will be contracted. Which means that it's automatic hold, and this part is contracted. Just second part. And with, of course, with forest, we can go leaf by leaf. We will something we know. So from this follows very about forests. Okay, so now I think I should say more relation of this with Chowanov homology, but for the moment, just on the level of combinatorics. So we'll be interested in special family of graphs, so-called circle graphs. They were analyzed by algebraic combinatorics, but as well by people in not totally interested in Vasily invariants. Circle graphs. So as the name suggests, we start from the circle. Then we draw arbitrary chords inside. Okay, so we draw some chords. They can intersect. Draw something nice. 1, 2, 3, 4. 5, 6. So we have some chords, and we form a graph just by the simplest intersection graph, meaning chords are vertices of the graph. If they intersect, they form an edge. So consider simple collection chords. Simple graph, associated simple graph, vertices, chords, this corresponds to crossings. So what is this, for example? It has 6 vertices. And every one with the nexus intersected, etc. I draw this so to get hexagon. So already with interesting independence complex, as we know in the S1 way. So, okay, so this is it. So the only thing I should mention here is that this may be interesting with respect to talk by Nick Z. When Maritania told me what he's trying to do in PhD, she said that she has one interesting graph, which is with respect to Chowanov this interesting. And it was just wedge of 2 hexagons. I mean, she has the called diagram or even a break, which was giving wedge of 2 hexagons. And she just said this is interesting homology. So I decided to find homotopy type of this. It was before Solva 11. I will say that you reduce by Solva just to 2 triangles. It will be very different. So after a big fight, I found or almost found that this is S2 wedge S3 independence complex of this. I was so fascinated by this calculation. All other calculations were showing spells or wedges of spells as well, but the spells have the same dimension. Here, the spells have different dimensions. So I was so fascinated with this that I decided with my target that we should form this as conjecture. That independence complex coming from simple graphs has homotopy type always wedge of spell. So unlike in Nick talks, he said that he doesn't yet feel confident to formulate conjecture, we did. So let it be formulated. Independence. Independence. Is homotopy equivalent to, I mean, either contractible, if not contractible, wedge of space. Okay. We don't have much time to define Chowanov homology, but still I would like to spend 5 minutes, or maybe even 10, to define Chowanov homology. So this is combinatorics. But we should see how to get to this combinatorics from Chowanov homology, and we cannot do this without definition. And it's really very close to definition. So let me see how much I can say. This. I will work with diagrams, leaving the Meister moves of topology aside. So first Kaufman bracket. Originally Kaufman bracket, Kaufman defined Kaufman bracket of the diagram, saying that he can resolve every crossing, formal variable A. So in this way, from every diagram, we can eliminate every crossing, and then for trivial and circles, he was putting minus a squared minus a to minus 2 to power n minus 1, because he wanted it for trivial not to be 1. So why this, for people who don't know this, that's easy, but why this strange substitution? Kaufman was trying A, B, D. And then second the Meister follows him to substitute B equal A inverse and this D. Doesn't come. Anyway, we'll use different, so this would be reduced Kaufman bracket. The standard one. But really, for Chobanov homology, it happens that you get different things when you categorify relate this Kaufman bracket and do something with Kaufman bracket, which is normalized for empty being 1, not for trivial, not for empty. So we do different bracket, but almost the same. Empty being equal 1, which will eventually give the diagram. The diagram is equal minus a squared. That is bounded. So this is unreduced Kaufman. Okay. How Zero was looking at categorification. First, he said that we should look at Kaufman bracket as state sum, that we do in physics. Kaufman was first to do this. So what is the state sum formula? Very easy. But we need some technical information. It should be state sum, so we should know what are states. So what is state? State is the function from crossing on the diagram into, and I will use A and B. B should be A inverse of A and B. So with two values, and convention is that when you have crossing drawn like this, then our function of the crossing B equal 1 will be interpreted as putting markers in this sense horizontally. And here when we put marker vertically. And finally, then we can, but of course, secondary, we can smooth this along like this. So we know what is Kaufman state. So this is A, and here's state by convention. Anyway, so we see what we get. We can write formula, state sum formula, with the sum over all Kaufman states. Considering all Kaufman states allows us to break every crossing using two possibilities. So this will be A to number of positive A markers, S inverse of A minus S inverse of B. And then we are left with some circles after we eliminate all crossing. But for circles, we know A squared minus A minus 2. And here will be diagram obtained by smoothing every crossing by confidence. Okay, so this is our formula. So what the Vilo was hoping would be that he knew about Chobanov homology, however, before it was written, that he will make homology when Kaufman states will form a basis for chain groups. So very close. However, he knew that we will not good if we have here polynomial, not monomial. So what he decided was formally make number of states bigger because the enhanced Kaufman state. So this breaks into two pieces. How to do this? How to visualize this? When you have circle, this more or less is a minus sign is different story. So if you break this and we call one circle positive and one circle negative, it will be a squared, it will be a minus 2 in this product. And adding additional function that was this b from our circles, when we smooth everything along S, so S into plus or minus. I will not write much. Below is enhancing Kaufman state. So this sum now will be equal to the sum over this capital S enhance Kaufman states. And this part will be the same, but this part will be A to number A squared, number of positive circles minus number of negative circles. Minus 1 will change. Now the A. So maybe this I will call them sigma. And the second part tau. Number of positive circles, number of A molecules minus number of B molecules, number of positive circles minus number of negative circles. So this is how we can rewrite this Kaufman state, but now we have only monomials. So because I don't have time, I will just say that this is already basis of Kaufman of Chowanov homology. The only thing we have to stratify this and define the differential. So just to make it shortly, how we break this SAB. So now our enhanced Kaufman state we have two parameters. Enhanced Kaufman state. The first method corresponds to this number of positive markers, number of negative markers, and the second corresponds to this total potential power of A. This is eventually what we are building is something having all the characteristics of the. So A is equal to S C state and B is equal sigma of S plus Y of capital S. Nothing. So this is how we break. And then differential, even if it is not precisely defined, it is already kind of giving a lot of information, is going to so maybe CAB chain group will be just standard SAB. SAB is base. So it's going from CAB to CA minus 2B. So B is constant, so we have for every B we have homology. Here it follows the divide by 2 sub, the divide by 2. Anyway, so what I'm trying to say is that now we have two indices, and what we did with Paretannia, we consider what is the possible maximal B and what is possible minimal B. This we call extreme, and then we work with fault rates. We translate the problem into circular graphs and some combinatorics, and with fault rate we succeed. And even better, we prove that not only this contracted wedge of spheres, but we can have at most 4 spheres and 3 of them of the same dimension. No generation to 5 is clear. It's tempting to say you have 4 spheres for 4 days, 5 spheres for 5 days. Absolutely no. You know very quickly. Who knows? We don't have concept of that. So thank you.
Oh, sorry, I'm not sure I understood the connection between this 9 threshold 9 that you have here with the independent, those computation that you had on the independence instead of complexity in previous 2
or how they are ready, yeah, because I didn't say. So we have A and B states. So how we really get to the extreme places? We try to have either power of A possibly maximal or possibly minimal. So let's say we work really with minimal, but everything is B. So then we have here all negative multiples and all negative circles. So this negative, so this B mean will be minus number of crossings from this part, from this part, and then this potential, and this potential sum. This potential sum of A, the maximum is minus n, minus twice the number of circles when we smooth the diagram along A crossing. So we know what is potential minimal degree of chain complex, minimal degree, potential minimal degree of homology. And this is the gradient we compute. Now what we do, we smooth everything. So now we smooth every crossing with B marker and with collection of circles. But you can think that these circles are still connected, kind of, there's trace of connection coming from crossing. And in our cases, usually we get one circle. We have no problem, one circle. And then the traces of all crossing are these chords. So this is really kind of original knot. And these are traces of crossings. And this is how we reach our circle graph. And then it's purely combinatorics.
So what does it correspond to? This 9.
But which one?
Number 9.
What's 9 here?
The polygons that you were saying.
Oh, this?
Yeah.
This is very easy. With 2 polygons, I will have check now. This corresponds to 3, in fact, 3 blades. Sigma 1, sigma 2 to power n, but n should be even. So n equal to k. 6. Anyway, this is just 3 blade pulse knot of type 3n. With 2 polygons, it is 4 blade and slightly more complicated. Still, one can write. But yes, one can translate, yeah, with some.
So then you probably have sort of collection of nodes, a collection of links that you can represent this way, and then you know everything.
But we don't have yet good characterization what you can get and what you can't get. We have consolidated with an extreme algorithm.
But for instance, you can have this kind of iterated torus nodes obtained this way, right?
I can have, for example, leaves, or I can have something which satisfies the main lemma. In fact, for 4 blades, this, where is my lemma? I erased this already. Anyway, this lemma that if there is a vertex, such that independence complex minus star of this is contracted in independence complex minus vertex. In fact, this is the main tool together with solver lemma we use. So we don't use discrete nodes now yet, but maybe.
What I was saying that you can just probably test these if you take, for example, a torus node, right?
Yeah, but we have up to 4 on. Yeah. So next torus node, yes, we can use the complete. Yeah. For
then,
some well-structured nodes, yes.
But then you have 3 2 torus nodes and iterated the next step also with 3 2 or something like that.
But then you raise the number of streams.
Yeah.
So generally, yes, but our problem is only for 4 blades. So for specific links, of course, you can do. I'm going to say that if you just draw standard diagram of torus node with n greater than 3, then to be contracted. But to have interesting thing, you have to choose different diagrams.
But I just torus node probably okay. I was thinking about iterate.
Yeah, I don't know. Yeah,
Because this would bring some additional structure.
yeah, absolutely. Interesting every family. Last 2 years we spent for this, so even for very small families, this complicated. We don't have very good general tools. And I was thinking a little bit about this discrete mole story, but it seems to be too general and
Okay.
I guess that there are some applications of one-node homology and non-homology to this is real and often.
we should ask Piotr Sylkowicz. Yeah, great for sure. John's polynomial, yes, Witten is fascinated by John's polynomial and by Chobanov homology. So,
But there are also some kinds of physics-like definitions.
for John's polynomial, very good definitions.
Just
For
for
Chobanov,
quantification, quantization of something.
for Chobanov homology, people who understand this at least partially claim that it is just Witten playing and not knowing yet where he's going. So, but yes, there are relations.
No, but there is even sort of formula, the definition of Chobanov homology, I don't remember.
There is
Exactly,
by
that using
Witten.
sort of quantization of something.
So we totally not understand that.
Uh-huh.
John's polynomial, yes, you can understand. It's Wilson loop that you go
Yeah,
around. That, this is okay, even if I don't understand, because he integrate over spaces without matter. But anyway,
Yeah.
this topologist complaint.
It's just a sort of integration of something that doesn't exist.
Yeah, exactly. But you have intuition, what is cancellations and what cancel, and then eventually you get John's polynomial. But for Chobanov, I think it's still what Witten is trying to do.
Any more questions?
Sorry, what is the advantage of Chobanov homology
Comparing what?
compared to the other ones?
Oh, it's a very nice structure. And as I said, my dream is that we measure some phase transitions, measure some phase temperature of some physical processes. And we know that John's polynomial is very closely related to Fock's model and Ising's model. So it's not totally dream, but still.
But actually, there are some examples of nodes that Chobanov homology can distinguish, and the other characteristic doesn't distinguish.
Yeah.
So that Chobanov homology is thinner.
But John's polynomial does.
Sorry?
John's polynomial.
No, but distinguish trivial not from non-trivial. For John's polynomial is conjecture, for Chobanov homology is proven.
Oh, I see.
So there's
Okay,
some
I see, I
improvement
see.
conjecture that versus.
And then there is another thing that even there is another generalization that probably much thinner called Cherednik algebras. And
An algebraic reference.
yeah, just started from the level of the representation field.
Okay.
There are
So I should
some-
advertise here another generalization, scale models. And you can say this is my colonel, but no, Witten became recently very much interested in scale models. He has some conjecture which was recently proven or almost proven about finiteness of the scale model of closed three-dimensional manifolds. So scale model became main topic of Witten followers. If you give some conjecture, then you have 10 people, very good one. Well, yeah.
Any questions? So let's thank the speaker again for that. Even though everything would be quite understandable and very, let's say, and